Solve problem 3.2 Fixed and moving positive charges. A positive charge of 4.5 microcoulomb is fixed in place. A particle of mass 6 grams and charge plus 3 microcoulomb is fired with an initial speed of 66 meter per second directly toward the fixed charge from a distance of 4.2 centimeters away. How close does the moving charge get to the fixed charge before it comes to rest and starts moving away from the fixed charge? We got a two particle problem here. We have two charged particles. This is charge number 1, charge number 2. The first charge is fixed. This is the origin of our coordinate system. Okay, so this charge is placed at the origin. So I'm going to call this point x equals 0. Yeah, it's not moving. It's a fixed charge and it has a charge of plus 4.5 microcoulomb. It's a positive charge. Now in our problem, we have one more charge. This is our second charge. It has a charge of plus 3 microcoulomb. It has a mass of 6 grams and it is moving. It's been fired towards the first charge, the fixed charge, with an initial velocity of 66 meter per second. Yeah, the initial position of the second charge, the moving charge, is 4.2 centimeters from the origin. It would move towards the positive charge, but its velocity would decrease because both of them are positively charged. This would experience a repulsive force from the fixed charge. As a result, its velocity would decrease. At some point, velocity would reach 0. It would stop there for a moment and it would turn back. So our question is to find the closest point. How close does the moving charge get to the fixed charge before it comes to rest? So at this point, this is the closest point, and at this point, our moving charge would come to rest. Okay, for a moment, just for a moment. Yeah, and we need to find this closest point of approach. Okay, let's write down the givens. So let's talk about fixed charge first. Fixed charge. We have magnitude of the charge for the fixed charge, QF. This is QF. Magnitude of the fixed charge. Yeah, this is the fixed charge, right? QF, and this is the moving charge, QM. Okay. So QF equals 4.5 microcoulomb. Micro is 10 to the power minus 6. So QF is 4.5 times 10 to the power minus 6 coulombs. Yeah, that's all about the fixed charge. And it is placed at the origin. The position of QF equals 0. Now about the moving charge. We have the magnitude of the charge. This is QM, and its mass. This is the mass of the moving charge. Its initial velocity v0 as well. Yeah. Okay. So QM is equal to 3 microcoulomb. 3 times 10 to the power minus 6 coulomb. Mass of the moving charge is 6 grams. Kilogram is the SI unit. Divide with 1000 to convert it to kilograms, or multiply with 10 to the power minus 3 kilograms. Now its initial velocity V0 is 66 meter per second. Alright, so let's have a look at the picture again. We have QM, the moving charge. It's a positively charged particle. It's moving towards another positively charged particle placed at the origin. It would lose kinetic energy because its velocity would decrease, right? So kinetic energy would decrease. potential energy should increase. So we can apply energy conservation theorem here. Energy conservation theorem. Conservation theorem for conservative forces. Yeah. Delta K plus delta U equals 0. Change in kinetic energy plus change in potential energy is always equal to 0. This is energy conservation theorem. Okay, what is delta K? Delta K is final kinetic energy. Final kinetic energy minus initial kinetic energy. This is the initial point and this is the final point. It's the final point. Initial point is di, final point is df, di and df. It has an initial velocity of 66 meter per second. What about the final velocity? Upon reaching this point, the charge would stop there for a moment, right? Because velocity would be 0. Okay, so the final velocity is 0. Final velocity V final equals 0. And the final kinetic energy, the equation for kinetic energy is half mv square. So the equation for final kinetic energy is half m final velocity squared. If you substitute the value of velocity, final velocity there, you'll get 0. Final kinetic energy is 0. Substitute back in this equation, you'll get delta K equals 0 minus Ki, or delta K equals minus Ki, minus initial kinetic energy. And what is initial kinetic energy? Half m initial velocity squared. Okay. So I'm going to call this equation number 1. This one equation number 2. Substitute equation number 2 in equation number 1. So delta K, we can replace delta K with minus half mvi square. Let's take delta U to the right side, minus delta U. Now what is delta U? It's the change in potential energy. We have this equation, we have learned this equation, delta V equals delta U over Q. Change in potential equals change in potential energy per unit charge. Cross multiply and find delta U, Q delta V. I'm going to call this equation number 3. Yeah, let's substitute equation number 3. Call this equation number 3. Let's call this equation number 4. So substitute equation number 4 in equation number 3. Minus half mvi square equals minus delta U is Q delta V. Yeah, I'm going to call this equation number 5. Let's cancel out minus 1. So that's our equation. Half mvi square equals Q delta V. This is for the moving charge, because we are talking about energy conservation for the moving charge. So mass of moving charge times initial velocity vi, right? Initial velocity, or v0, yeah, v0, right? I'm going to change it. v0 squared, charge of the moving charge, which is Qm, and the change in potential. Okay, in this picture, QF is not moving, and QF is creating a potential around it, right? And QM is moving in that potential. Okay, so let's say this is QM, fixed charge QF. because of its presence, it would create a potential around it, right? Um, Different potential values for different points around it, different values. Yeah. Let's say this is QM, the moving charge QM, and QM is moving in that potential, right? Let's say starting from here to here, then it would come back. So QM is moving in that potential of potential created by QF. Yeah, this is QM. Yeah, okay. So the potential difference is due to QF. QF is our main charge here. So delta V equals final potential minus initial potential. Change in potential is final potential minus initial potential due to the fixed charge, right? It is creating potential around it. QM is also creating potential, but QF is our main charge here, and QM is moving in that potential region. So delta V equals VF. How do you write VF? Okay, let's go back to this picture. Yeah, this picture. This is the initial point, DI. Let's say this is the final point, DF. So VF equals final potential, right? This is the final point. Let's say the distance from here to here is DF. The equation will be K times the main charge, which is QF over DF. Now, how do you write potential for the initial position? This is the distance, right? DI. So K, the main charge, which is QF, divided by DI. Okay, let's substitute VF and VI in our equation. KQF over DF minus KQF over DI. I'm going to call this equation number 6. Equation number 6. Now we have the equation for delta V. I'm going to substitute equation number 6 in equation number 5. Substitute equation number 6 in equation number 5. Half, left hand side is half m, mass of moving charge, times initial velocity of the moving charge squared, is equal to q delta v. Q of moving charge times delta v is substituted kqf over df minus kqf over di. Our question is to find df. So solve for df. That's our next objective. So I'm going to switch LHS and RHS. QM times KQF over DF minus KQF over DI equals half mm times V0 squared. We have K and QF common in these two terms, so take it outside. QM times K times QF. If you take K and QF outside from the first term, you have 1 by df minus 1 by di equals 1 by 2 mm. 1 by 2 mm times 1 by 2 mm. 1 by 2 mm times 1 by 2 mm. 1 by 2 mm times 1 by 2 mm. 1 by 2 mm times 1 by 2 mm. 1 by 2 mm times 1 by 2 mm. 1 by 2 mm times 1 by 2 mm. 1 by 2 mm times 1 by 2 mm. 1 by 2 mm times 1 by 2 mm. 1 by 2 mm times 1 by 2 mm. 1 by 2 mm times 1 by 2 mm. 1 by 2 mm times 1 by 2 mm. 1 by 2 mm times 1 by 2 mm. 1 by 2 mm times 1 by 2 mm. 1 by 2 mm times 1 by 2 mm. 1 by 2 mm times 1 by 2 mm. 1 by 2 mm times 1 by 2 mm. 1 by 2 mm times 1 by 2 mm. 1 by 2 mm times 1 by 2 mm. 1 by 2 mm times 1 by 2 mm. 1 by 2 mm times mass of moving charge times initial velocity of the moving charge squared. We need to find df, so let's take this whole term to the left side. 1 by df minus 1 by di equals mmv0 squared over 2 times k times qm qf. We need to find df, so take minus 1 by di to the other side. So 1 by df equals mmv0 squared over 2k qm qf plus 1 by di. So 1 by df equals, solve the right hand side, cross multiply, mmv0 squared di plus 2k qm qf over 2k qm qf di. We have 1 by df, we need to find df, so flip the right hand side, 2k qm qf di over mm v0 squared di plus 2k qm qf. Okay, that's the equation for df. Now let's substitute the values. 2 times k is 9 times 10 to the power of minus 9. Moving charge is 3 microcoulomb, so 3 times 10 to the power of minus 6. Fixed charge is 4.5 microcoulomb, so 4.5 times 10 to the power of minus 6. The initial position di is 4.20 centimeters. 4.20 centimeters. To convert it into meters, multiply with 10 to the power of minus 2 divided by mass is 6 times 10 to the power of minus 3 for the moving particle, kilograms. Its initial velocity is 66 squared times, again initial position is 4.20 times 10 to the power of minus 2 plus 2 times k is 9 times 10 to the power of minus 9. Moving charge is 3 times 10 to the power of minus 6. Fixed charge is 4.5 times 10 to the power of minus 6. Okay, you'll get 0.00761 meters, or multiply with 100, 0.761 centimeters. Okay, so that's our df. Or the closest point the moving charge can reach is 0.761 centimeters away from the fixed charge.